Okay, so this is, I think we're recording, right? This is Physics 1A for March 15th, and today we are going to be talking about two-dimensional motion. We're going to be discussing displacement, velocity, and acceleration in two dimensions. We'll talk about projectiles, which are just things like baseballs, golf balls, arrows, things that are thrown through the air. We'll do some problems, and if we have time left over, we'll talk about number 4 there. I don't think we'll have time for that, though. That'll probably be next time. All right, so let's get right into it. So we've defined the concept of displacement previously, but we only did it in one dimension, so let's do it in two dimensions. So let's start off by drawing like an XY axis right here. And we'll call this direction X, call this direction Y. And now we want to describe what displacement means if you're moving across a plane, or like across the surface of the Earth, for example. Okay. So first thing we'll do is we'll just pick 2 points. We'll pick one point right here, which will be our initial position, and I guess here, let's move this over a little bit. I want to be able to draw these vectors pretty clearly. So put one right there. Let's say that that's our initial position. Let's say we moved from over to here. Okay. So we start at this position right here in the bottom, and we move to this position here. Okay. Our displacement is going to be a line that we draw basically from here to here. That's going to be what our displacement vector is going to look like. All right, let's use a different color. Turn off ink to shape. Go full screen. So our displacement vector is going to look something like this. Okay. And for displacement, we're going to label this one to be delta R. Okay. And so delta R is going to be what we call displacement. And we'd also like to define position as well. So if we want to define the position of this point right here, we could use like the XY coordinates, for example, of that point. And if we wanted to represent those XY coordinates as a vector, we could represent them like this. So if I draw a line from the origin out to this point right here, then I'm going to say that's going to represent my initial position. So I'm going to call that R0. And just say that R sub 0, this is going to be our initial position. And position is always just the location of where you are relative to some fixed point. So the fixed point in this case is the origin. XY coordinates would give you the position. And then we can move to a final position. We use green for that. The final position would be from here up to here. Actually, green we're already using blue for that. So that is going to be our final position. And the thing that's going to connect all of these vectors is just going to be this equation, that delta R, the displacement, is just equal to the final position minus the initial position. This definition is exactly the same as what we used in one dimension. But, now you're moving in two dimensions. You move from this location to this location. And that's what displacement is. Yeah, what else to say about it? That's how it's defined. In general, we can describe, let's just pick one of these here. Let's say that for R naught right here, let's say that the XY coordinate of this is X sub 0, comma, Y sub 0. And let's say that the XY position of the final location is X final, comma, Y final, like this. Then we can define each of these vectors using unit vectors if we want to. We can say our initial would be equal to basically X naught I hat plus Y naught J hat, where X naught and Y naught are going to be numbers. It could be like, 4 comma 5 or something like that. And we can go through and we can do the same thing for each of our vectors. So our final would be given by whatever the final coordinate is times I hat plus the final coordinate times J hat. And then delta R could write it like this. So delta r would be equal to the change in x times I hat plus the change in y times j hat, or the other way to write it out in terms of all the individual coordinates would be delta x would be x final minus x initial, just the x displacement times I hat, and delta y would be, y final minus y initial times j hat. Okay. Now, what we can do is, if we know what the displacement is, we can find the velocity. So for example, imagine that we have an object that moves between this point and this point. Maybe it's just a person that's walking or something like that. So let's draw a person on here. What's the color I haven't used? Purple. So let's say that there's a person and they walk from this location up to this location here. And let's say that the time interval that it takes for them to move from that position to that position is delta t. So you say maybe it takes 10 seconds or something to move between those positions. Then we can start to define some vectors like we did before, such as we can define the average velocity. Average velocity is just going to be, we'll use this symbol, v with a vector symbol above it. Average should be equal to basically just the displacement delta r divided by the time. From this equation, it should be pretty clear that the direction of the average velocity vector is going to point in the same direction as the displacement vector, because time is a scalar. So the direction of that vector is going to point just along the displacement vector, like this here. That's the direction of your average velocity. And then when we compare it to this equation right here, the other way that we could write this is delta x times I hat divided by delta t plus delta y divided by delta t times j hat. That would be another way to write what the average velocity is. Just you would take the rate at which the x is changing times I hat plus the rate at which the y is changing times j hat. And then what we can do is we can take, if we want to find the instantaneous velocity, we would say that that's going to be equal to the limit. So you just use v for instantaneous velocity and say that this is equal to the limit of delta r over delta t as delta t approaches 0. Or written in another way, the instantaneous velocity can just be written as the derivative of the position vector, basically, the rate of change of the position vector, like this. And if we write it like that, and we say that kind of like in general, the position of an object in 2 dimensions, the position of an object is pretty much just given by like 2 coordinates, right? X and y. So if we want to write in general what a position vector looks like, this is an example of a specific one, but in general the position vector would look like the x coordinate times I hat plus the y coordinate times j hat, for example, in 2 dimensions. If we use that on this equation right here, what that tells us is that the velocity is going to be equal to the derivative of this thing. So let's just, I guess we'll write the whole thing out. The time derivative of x times I hat plus y times j hat. Scroll down just a little bit. And then we can move this derivative into this expression right here to say that the velocity is going to be equal to dx dt times I hat plus dy dt times j hat. And then we can identify that any vector in general, like this velocity vector, can be written as the x component of the velocity multiplied by I hat plus the y component of the velocity multiplied by j hat. And then we basically just compare these 2 equations, compare this to this, and compare this to this. And we end up finding out that the x component of our velocity is given by dx dt. So the takeaway from these 2 equations is that v sub x is equal to the time rate of change of the x-coordinate, or dx dt, the x derivative. And we find that v sub y is equal to the time rate of change of the y-coordinate. And I'll stop for a moment. Does anyone have any questions about how we got to here? Repeat x and y again. Which part? Just what I said about, so the x-coordinate of the velocity for an object is going to be equal to the rate at which the x-coordinate changes. And the y component of the velocity will be equal to the rate at which the y-coordinate changes. Is that what you want me to repeat?
Yes, Professor, thank you.
Okay, so what this tells us, if you kind of look at this and think about it, if you look at this equation right here, it's saying that to find the instantaneous velocity, you need to take the derivative of a position vector. And to me, when I look at this equation, that seems kind of complicated because a vector is something that's represented by two coordinates, right? And in your calculus class, when you take derivatives, you don't take derivatives of vectors, right? What do you usually take derivatives of in calculus? Equations, but more generally, what do we usually call the types of equations that you're taking derivatives of? It's usually functions, right? That's the word I was looking for, at least. And those functions that you use, they don't have vectors in them. Would you all agree? There's no vectors in those functions. It'd be something like, you could have something like this. X is equal to 3t squared. That's a function. That would be x as a function of time, right? And you easily know how to take this derivative, right? If I had an object that was moving according to this equation, then it says down here that if I want to find the x velocity, v sub x, as a function of time, all I need to do is to take the derivative of this, which is really easy. Just bring the 2 down in front. 2 times 3 is 6. Subtract 1 from the power, right? That is really easy to do, right? So the power of what we've just did here is that the final result tells us that if I want to know something about the x-coordinate of an object's velocity, I just need to take the derivative of the motion in the x direction. If I want to take the y component of the object's velocity, I just need to take dy dt. This basically means that you can separate the motion of an object. I'll write this over here on the side. You can split the motion of an object moving in 2 dimensions, or 3 dimensions too. We're just going to do 2 dimensions today, but everything I'm saying applies to 3 dimensions. You can add, we can make all these equations more complicated by, for example, starting from the very beginning. We could have said delta r is equal to delta xi hat plus delta yj hat plus delta zk hat. And then everywhere else you'd have average velocity would have a delta z over delta t. This equation would be the same. Your z component of velocity would show up down here, and you can pretty easily guess what it would be. It would just be dz dt. So extending this to 3 dimensions is not difficult, but we're not going to worry about that today because almost all the problems you'll see in this class will be in 2 dimensions. Mostly because the motion of any object, even if it's in 3 dimensions, can be basically forced to be in just 1 dimension as long as it's moving kind of in one plane, like a projectile. Anyway, so you can split the motion of an object moving in 2 dimensions into separate motions So that's what this means. This means that the x velocity of the object has nothing to do with what's happening in the y direction, and the y velocity of the object has nothing to do with what's happening in the y direction at all. They're completely separate from each other, which is pretty amazing. And it really makes solving a lot of problems quite a bit more simple than they would be, just because of the fact that we can do this here. Okay? All right. So we've got this definition of what the x component of velocity is, but what does it mean? What does the x component of the velocity of an object actually mean? So let's think of an example that we're going to be getting into here in a second, where let's say I've got a surface right here, and on this surface, let's say that I take a ball. So I'm standing right here, and I take a ball and I throw it through the air. So I launch it in the air in this direction with some initial velocity that's a vector, right? I think you guys know that the motion of this object is going to be, let's see how well I can draw this. It's going to do something like this. Really bad. It doesn't look great. Let's extend this. Oops, I thought I clicked the blue one. Extend this way. So the motion of the ball is going to look something like this, right? Now, this is the path that the ball traverses, right? This line right here represents the path, right? And if we think about what the ball's doing as it moves along, let's say, for example, when the ball gets to like right here, at that location, what is the direction of the velocity of the ball going to be? So if I throw a ball and it flies through the air like this, at this point in time, what's the direction of the velocity vector going to be? How would I know how to draw it? The angle between the ball and the ground may show up, but I just want to know, just simply, Chris, what's the direction at this location of the velocity of the ball? Is it up? Is it down? Is it left? Is it right? Is it something else? Take the limit of the secant line. Tangent line to the slope. That's exactly right. Both of those answers, what Andrew said and Kelvin said, are right. Right, so if I draw a line that's tangent to the path, like this, I don't know if that's perfectly tangent, but maybe, that's what the velocity is going to be at a single point, right? All right. So the velocity vector is always going to be tangent to the path. Okay. So for example, right here, the velocity vector would point kind of like that. And even right at the very beginning, the velocity vector is tangent to the path, right? Okay, so what do I mean by Vx? Well, I mean by Vx similar to what we did with our force things, that we can break up this velocity into components. If we define this to be the positive y direction and we define that to be the positive x direction, then if I want to find the components of this, what I would do is, I'd make an x component and it would basically point parallel to the ground. And I would make a y component and it would point perpendicular to the ground. This would be what we call v sub y, and this would be what we call v sub x. Now there's a natural way to kind of visualize v sub x, which is that if, for example, we throw a ball and it's sunny outside, then the sun is going to cause this ball to cast a shadow, right? And because the sun is so incredibly high up in the sky, that means that the rays of the sun basically kind of shine straight down like this, right? That's how the rays of the sun are going to go, because the sun is, so far away from us, 8 light minutes away. Okay, so what's going to happen then is that this ball is going to project a shadow down here. Oops, I wanted to use black for that. This ball is going to project a shadow down here. Right? And at some later time, the shadow is going to be right here. Now, the rate at which the shadow moves across the ground is basically the same thing as Vx. Does that make sense? Because the light from the sun just projects straight down, and the ground, at least in the picture that we're using here, is basically like a one-dimensional line, and the rate at which that shadow moves to the right is the same thing as the x velocity. So that's one way you can think about what we mean by x velocity, is it's the rate at which this shadow would move across the ground. Does that make sense? Okay. What's the y velocity? We can't come up with like a nice shadow thing for the y velocity, but we can just say that the y velocity is basically the rate at which the object is moving up and down, okay? At this location, the ball is moving upwards, so we say the y velocity is positive. But later on, the ball is moving downwards, like here, right? So we would say the y velocity here was negative. So this would be positive y velocity, this would be negative y velocity. And somewhere in the middle, of course, right here, the velocity in the y direction would be equal to 0. Right? Okay, so that's what we mean by these things, these components. And of course, the way in which we're going to find these things is we're going to have to know something about the angle that's made right here. Because if we know what that angle is, we can write what Vy and Vx are, not in terms of derivatives, but instead in terms of the angle, right? We can say v sub x is going to be equal to v times the cosine of theta, and v sub y is going to be equal to v times the sine of theta, for example. All right? So we're going to have multiple ways to find these things. In a problem, if you're given a function, you're going to use this method. In a problem, if you're given like an angle, like I think Chris was mentioning here, in this problem, you'd like to know, for example, what this angle right here is. Maybe you call it theta initial or something like that. If you're given this kind of information, you're going to use this method, which will usually be what we do. But sometimes we'll also use this method to find the x and y velocities. But nonetheless, it's important to understand that you can find the x component of velocity by taking the derivative of the x coordinate, the rate at which the x coordinate changes. All right, the next thing to do is to talk about acceleration. So for acceleration, what we say is just average acceleration. We can define just as we did in the last chapter. We can say that average acceleration is going to be equal to the rate of change, or the delta v, the change in velocity, divided by the change in time. And of course, we can also write this as a vector as delta v sub x over delta t times I hat plus delta v sub y over delta t times j hat. And then we can employ the same trick that we did before to say that if I want to find the instantaneous acceleration, we just say a is equal to the limit as delta t goes to 0 of this expression. And of course, this is just the derivative. So instantaneous acceleration is given as the time derivative of the velocity vector with respect to time. So that's our definition of instantaneous acceleration. And then, of course, we can write this out more fully because we know velocity is equal to vx times I hat plus vy times j hat. Throw that in here, then acceleration becomes the derivative of vx with respect to time plus the rate of change of the y component of the velocity with respect to time times j hat. Right? And we can go really even further. Well, okay, let's before we do that, this tells us that the x component of the acceleration is equal to that quantity, the rate at which the x velocity changes, and the y component of the acceleration is equal to the rate at which the y component changes of velocity. And then we can go one step further, because we said above that vx was equal to dx dt, and vy was equal to dy dt. So putting all those together, this one here, a sub x now, since it's the derivative of the velocity, and the velocity is this, then what we can say is that a sub x would be equal to the derivative of this thing, which is dx dt. And then this thing we know to be the second derivative, right? This is d2x dt2. And of course, by comparison then, the y component of the velocity will be equal to the second derivative of the y component with respect to time. That's ay, and this is ax. So once again, notice that even with acceleration, the kind of dynamics associated with acceleration can also be split into two dimensions, just like with velocities, okay? So what the object does in the x direction really has no effect on what it does in the y direction. Does that make sense? You can always separate these things out. And that's what we'll do with all the problems we do. We'll always be splitting everything into kind of two problems. Motion in the x direction, motion in the y direction. And yeah, that's the approach we'll take for all the stuff that we'll do today. So, anyone have any questions? To kind of summarize what we went through right there, we said you can define a vector that's called position. And then once you define the position vector, you can define a vector called velocity by taking the derivative of that. And then once you find that, you can find the acceleration by taking the second derivative of the position, which is the same thing as the derivative of the velocity vector. That's really all that we just did. We just basically stated that. The position, velocity, and acceleration of each object is related to, you basically just take a derivative again. And if you wanted to, you could take another derivative of this, right? We could keep playing this game, right? We can keep taking derivatives, right? In a lot of problems, acceleration is going to be constant for you. So taking one more derivative is just going to give you 0. But there's also a vector that's called jerk. I don't know what symbol they use for jerk, so I'll just write jerk and put a little vector symbol over it. And jerk, if you could guess pretty easily, is going to be the derivative of the acceleration, the rate at which the acceleration is changing. So this doesn't really show up too much, but sometimes you'll have a problem that might mention that this thing is called the jerk. I think it's called jerk because when your acceleration changes very quickly, such as, for example, this happens if you're riding in a rocket, like when people get shot up into space with rockets. Not only are you accelerating, but the rate at which you're accelerating is increasing, and it has the effect of putting a lot of g-forces on you. I don't know if that's why it's called jerk. I don't know where the name jerk comes from. But then again, I don't really know where the name velocity or acceleration comes from. They're probably derived from Greek words or something like that. All right. So we've got all the terminology. I think we're good to kind of start looking at applications, start looking at projectiles. Does anyone have any questions? What time is it? 2:20. Okay, we got time. All right. So the main application we're going to see in this chapter for motion in 2 dimensions is going to be, is there more after jerk? You know, probably, right? There should be, right? I don't know if they have names. Oh, I want to say one other thing, because you might notice something come up. Either, I don't think the textbook talks about this, but if you go and like look for some information about physics on the internet, you might see a different way in which some of this stuff is notated. And I'm just going to show you what that notation looks like. So let's say we just have something where like it's only has the x direction associated with it. So like, I don't know, something like this. All right. So let's say you have an object and it moves according to this equation right here. And I need to throw some units in here, but let's not worry about the units for right now. Okay. So the symbol dx dt, what did we say that was equal to? What is dx dt equal to? If this represents the x-coordinate of an object, what does dx dt give me? It gives you velocity, but what type of velocity is it going to give you? What velocity is it going to give you? It gives you the, Vx, right? This is Phys of x. There's another way this is commonly written, and it's basically just x with a dot above it, okay? The dot means to take a time derivative, right? To compare that to something else you've probably seen before, in your math classes, you might write something like f of x is equal to, I don't know, let's use sine of x, right? And then if I write f prime of x, everybody knows what that means, right? That means to do what? What does f prime mean? The first derivative with respect to x, right? So this means take an x derivative, right? This means take the derivative of the function with respect to x. And if I write f double prime, that means to take the second derivative, right? Which we write as d2f dx2. And you could get by without even writing the x, right? F double prime would just mean it's the same thing, right? So the prime is a spatial derivative, right? It's a derivative with respect to the x-coordinate, which is a spatial coordinate, right? By spatial, I just mean moving. When we move around in space, we change our coordinates, right? So if you want to take a time derivative, that's what the dot represents. Okay? So if I write down x with 2 dots above it, what do you think that represents? The second derivative with respect to time, though. See, one thing you're all not saying, and I'm saying this only to be nitpicky because it matters. You see the difference is that over here, you're taking, it's not just the derivative with respect to, it's the, this is the specifically the derivative with respect to x. That's what the prime thing means, right? And this one means to take the time derivative. So what would this be then? If it's the second derivative of x, what does it represent? Ax, yeah. We don't really use a capital A usually for that, but yeah, a sub x. So this would be the acceleration, and this just means take the second derivative. So d2x dt2, right? So you may or may not see this kind of terminology, but now you've been introduced to it, so if you do, you're not going to be confused. Because like you're going to see some equations, like I'll give you an example of one. Net force is equal to mass times acceleration, right? That's an equation that we're going to have show up in the future. You've all seen this before. It's Newton's second law, right? But you probably also know that you can write it in terms of components as net fx is equal to m times the acceleration. Well, we can write this in a different way now, right? We can actually write it as m times x with two dots above it. So this is the kind of thing you might see if you start, going looking at forums or Googling questions and you're trying to solve for answers. Sometimes some people will give what I would say is probably like kind of too high of a level of an explanation, but this just kind of shows up in other textbooks. Someone asked a question, Chris, you asked, so in physics we don't use the prime thingy. Yeah, Summer, you can write d2x dt22 if you want to. This is just a nice little shorthand notation for it, okay? We don't use the prime thing in physics. I mean, you can. Yeah, you can totally use the prime thing in physics. There's nothing wrong with that. I know what this means. You all know what this means, right? If I write f prime, it means take the first derivative with respect to whatever variable shows up in here. But in physics, we try to separate out the time variables from the spatial variables. That's all that I'm trying to say here. And I think I'll just move on because I was just trying to introduce you to it. I do know that some of the other professors at this school will use this type of notation. That's also why I'm introducing it to you, depending on who you take. I don't sit through all their lectures, but I've walked by and I've definitely seen this type of notation on the board. So, now you've been exposed to it. I don't think you're going to see it much in the textbook, but it will show up in other places. Okay. Mastering physics? I really don't know, Patty. I don't think it will, though. It might. That's exactly right, Chris. The dot only works with time. I believe that this notation was originally introduced by, I think this is Leibniz, but it could be Newton. I can't remember who did this notation first, but I think it's Leibniz, maybe Newton. I'm not sure though. Okay, so now we want to talk about projectiles. So let's define what a projectile is. This is basically anything that gets thrown through the air, and it falls under its own weight. So it's anything that's thrown or shot. And the stipulation is that it can't have its own type of propulsion for the type of motion that we're going to talk about. So examples of things that would be, I'll tell you things that are and things that aren't. So examples of projectiles would be things like a baseball that's hit through the air, a football. We will talk about drag, which is air friction, Andrew, in this class, but probably not today. We'll talk about it later on. Well, we'll talk about it a little bit, but for all the stuff we're going to do today, we're going to ignore drag. So like a baseball that's thrown through the air, a football that's thrown through the air, an arrow that's shot out of a bow and arrow, a bullet that gets shot out of a gun. Bullets don't have their own propulsion, right? Things that are not projectiles. Would be something like a rocket. Whether it be like a rocket that's fired to send supplies to the International Space Station, or whether it's a missile. I guess a missile would be another thing to put on here. Because, missiles usually have their own type of fuel that they can use to burn to, navigate and stuff like that. Yeah, an airplane would be an example. That's a really good example. An airplane is something that's not a projectile. It just kind of it An airplane basically finds a balance between the lift force that's placed upon it, which comes from drag, and that helps to keep in the air. So the motion of an airplane is not going to be a projectile. But literally anything that gets thrown or shot or dropped, anything like that is a projectile. And if we want to describe what this motion is like, I think what I'll do for this, just to kind of highlight a lot of the details of it, is we're just going to go to this page right here. So I want to show you this website. We haven't used it yet in this class, but we're going to be using it more and more. So this is the website. I'm going to copy paste this. You can feel free to go to the website yourself and play around with what I'm doing right now, if you want to. But this is a really nice, it's a really nice website that has all sorts of simulations for physics, chemistry, math, or science. I'm sure many of you have seen these things before, other classes. And what we can do is here, I can click on physics. I'm going to get rid of all these checkboxes here because I just want to talk about motion. And you can see that there's a lot of different little simulations and things to play with. I think if you're someone that wants to learn by kind of manipulating and playing with things, I think this is a good thing. There's something with gravity and orbits that we'll look at later. There's this balancing act thing. There's this skate park thing that allows you to look at some energy stuff, which we'll be looking at later. But today we're going to look at this one. There's also one on vector addition. These simulations, I think, should run on pretty much anything. It's HTML5, so I've never tried it, but it might run on a phone. Should run on a tablet, I would think. Right? Doesn't HTML5 run on phones? All right, so here's what we have. We've got a little cannonball, or cannon, and we can manipulate the angle at which that it gets launched, right? We can also have air resistance, although to begin with, we're going to turn off air resistance. We'll add it in later. You can also change, I think, what the object you're shooting is, but we're going to shoot a cannonball. We've got a mass right here, a diameter, and yeah, so let's just fire it real quick and just shoot it and see what happens. So that motion right there is what we call projectile motion, and we can do it again. And we can see that it traces out a path. It has some features. It has this apex point right up here. This is the part where we say maximum height. Yeah, summer. That would be a projectile, sure. Yeah. A piece of fruit falling from a tree. Yeah. Basically, as long as the object that's moving can't make itself move, you know, as long as it can't deliver some force to change its motion. All right, so you've got this top point right here. And we can also, what's really nice about this program is we can look at velocity vectors. But before you do that, I just want to do something real quick here. This thing was shot at 65 degrees, right? What do you think is going to happen if I put it down to, like, let's say, I don't know, let's say we shoot it from 40, let's do 40 degrees. Do you think the ball is going to go farther or shorter if I shoot it at 40 degrees? It won't be in the air as long, right? But everyone seems to think it'll go farther. Let's check, let's see. Looks like your intuitions are correct. It goes quite a bit farther, maybe, I don't know, 20% farther or something like that, right? Okay, let's undo those two. Let's go back to 65. Let's shoot that one again. What if I go down to 25? Is it going to go farther or is it going to go shorter? Shorter? Too low? Shorter? Okay, let's see. Oh, look, it went the same distance. Doesn't seem like anyone thought that was going to happen. Let's try it again to make sure that I didn't cheat something. So we'll erase these. So if I go at 65 and I shoot it, we can actually move the marker to that same location if we want to. Looks like it went about 25.3 meters. And then if I go down to 25 and I shoot it, get exactly the same. Now this shouldn't surprise you. This isn't that surprising, right? That there's some way you could shoot one upwards and one way you could shoot one low and still get to the same location, right? Because I'm sure everyone here has at some point in their life played a game of catch with maybe like one of your younger siblings or niece or nephew or something like that, right? And you know that if I want to, like if I'm standing here where the cannonball is and I want to throw a ball to this position here, there's multiple ways to get to that location, right? I can throw it way up in the air so it comes back down and it lands on the person like this. or I can throw it kind of low into the ground. Which one of these will take less time? Which one will get to the person faster? Yeah, the lower one, right? So if your goal was to get to them as fast as possible, you throw it this way. If you just wanted to throw the ball way up in the air, you could throw it this way, right? Okay. So let's see if we can figure out why that's the case. So 65 and 25. What's special about those two angles? 65 and 25. What do you notice about the two of them? The sum is 90, exactly. So let's try another set of angles that add to 90. Let's try 70 and 20. Let's see if we get the same thing. So 70 should go shorter, right? Just come somewhere like right here. And if we try 20, oh, we can't do 20. Okay. Let's do 60 and 30. So here's 60. 60 should go a little bit farther, right? Doesn't really matter if I move this thing. So there's 60. And if I put it at 30, boom, same thing should happen. They go exactly the same distance. Okay. What do you think is going to happen if I add an air resistance? You think that's still going to be true? With no air resistance, as long as the two angles add to 90, they'll have the same range, basically. So let's see what happens with air resistance. We'll reset both of these. Oh, you know what we'll do here? Let's do this. So let's reset them. We'll fire one time with 60 degrees like this, with no air resistance. Now if I add an air resistance, that's going to make it so that the faster the ball goes, the more resistance or force that it feels. It's definitely going to go shorter, right? Much shorter, as you can see, right? And the shape has kind of changed. I don't know if you noticed, but the shape of the blue line right here is what we call a parabola. We'll prove that that's true here in a second. That blue line's a parabola, but this one no longer really looks like a parabola, right? It's kind of a squished parabola in a way. All right, let's go back down to 30 and let's see what happens. There it goes. It goes much farther. I think that's kind of what people thought, right? Yeah, someone said shorter on the higher one, right? And that's just because it's in the air longer, right? It has more time to get slowed down by the air. Yeah. Okay. Let's take air resistance off because that's not really what we're trying to learn about today, but it is interesting to see how it affects things. Okay, so let's start to look at the... unless you include the vector of the wind. You don't even need to have wind to have air resistance, though, right, Andrew? Air resistance is there even without wind. Like, I can move my hand around in the room and I can feel the air slowing my hand down in a way, right? So let's start looking at the vectors associated with this. Let's start off with the velocity vector. So let's shoot it at 65, and now what it's going to do is it's going to show a velocity vector as the object moves. And we can, if we want to, at one point pause it and kind of indicate what I said before, that the direction of the velocity vector is going to be tangent to the path, right? So here it's tilted down because the object's moving like that. Eventually you get to the very top. I actually paused it right at the top because that little green dot, that's what represented the apex, right? And you can see that velocity vector at the very top is completely parallel. And then it continues down like this, like that, to there. So yeah. You might also notice, if you kind of look at the length of this vector right here, when it starts, that when it gets to the very end, the vector is about the same size. It turns out that if you launch an object from one location and it basically lands on the same elevation, same altitude, that the initial velocity that it's shot at is going to be the same as the final velocity. That's something else that we can prove mathematically if we want to. Okay. So that's the velocity vector. But what I said is that for all the stuff that we do in this class, we can always split things into components, right? And by looking at the components, this motion suddenly becomes a lot more simple. When we split it into motion in the x and y directions separately, the velocity vector, you start to see some patterns with it. So let's shoot this right here. So now what we have is an x velocity vector. I'm just going to keep shooting it, which is the one pointing to the right here. And we have a y velocity vector, which is the one that starts off pointing straight up. It drops to 0, and then it becomes negative, right? That's the y velocity. Gets small, comes back down. Likewise, let's see if we can... here. Let's use this for a second. Just to pick another point over here that's the same height. So let's also look at this. So if we shoot this... I didn't quite pause it. Okay, I paused it there. So let's look at that one right there. If we measure this vector here, right? and we come over to basically the exact same point. So the length of that vector is represented by this piece right here, okay? So let's see what happens when the ball gets to exactly this location. See if I can stop it right on it. Pretty close, right? At this location, which is the same elevation as it was on the other side, the size of that vector is basically exactly the same. So this motion is very symmetrical about this point right here. The ball, when it's shot on the way up, here, let's erase all this stuff. The ball, when it's shot on the way up and on the way down, oops. If you pick the same elevation, it's going to have the same y velocity, just in the opposite direction, right? Okay, what else do you notice about this? What's happening with the x component of the velocity here? What's happening with that? It's constant, right? That's something you have to remember about this, that the horizontal velocity, or the x velocity, is not affected, okay? Now that wouldn't be true if we added an air resistance, right? Just to indicate the difference. If we add an air resistance, the x velocity vector is going to change, right? Does that make sense? Starts off kind of long and it gets a little bit shorter. It doesn't go through nearly the same amount of change as the y velocity vector does, which tells you that the deceleration that the ball experiences due to air resistance is nowhere near as big as the acceleration that the ball experiences due to gravity. Right? So gravity is definitely more of a force that controls this motion than air resistance. And you can also see that if you put in the acceleration vectors. Let's turn off this. So there's your acceleration vector. And in the x direction, you can see what it's doing when we put on air resistance. All right, let's turn off air resistance again. And now let's just look at the acceleration vector when there's no air resistance. That's not right, Summer. Vy changes direction, but it also changes magnitude because it's affected by an acceleration. Vy is not constant. No. Okay, so there's our acceleration vector. What do you notice about that vector? Does it look like it's changing? And this is the total acceleration vector too, right? Okay, does it look like it has a y component? Has a y component, right? Does it have an x component? No x component, right? Okay, so we've now basically hit on all of the major points just by playing around with this, clicking some different things here. We basically hit on all of the major points about parabolic or projectile motion, okay? And these are what they are. I'll write them all down when we go back to the other page, but the motion is constant in the x direction. The velocity is constant. The acceleration is constant in the y direction. The velocity in the y direction reaches 0, right, when you get to the top up here. Wish I could go backwards. I can't. But the velocity when you get right to the apex right here in the y direction drops to 0. It's positive on the left side, negative on the right side. And the other thing we figured out was that if you launch an object from 65 degrees and an object from 25 degrees, that they'll go to exactly the same range. That is to say, when the angles add to 90 degrees, you get the same range. The range is basically how far the object travels in the horizontal direction if it launches from the same elevation that it lands at. And that's pretty much it. You're more than welcome to come in here and play with this, and there's all kinds of things you can do. For example, we can do things like we can I guess. Oh, I thought you could change. Oh, here it is. Yeah, you can change the thing that you launch. So instead of launching a cannonball, you can launch a pumpkin, for example. Oh, this one actually allows you to get all kinds of angles. Now that's interesting. So like you can shoot a pumpkin. You might be like, oh, what does that matter? Well, it matters when you throw in air resistance, because the way that a pumpkin is going to be affected by air resistance is going to be different than the way a cannonball is going to be affected by air resistance. Looks like a cannonball is less affected, which should make some sense, right? Can I show all vectors at once? Yeah, I can do that. I'll leave the force vectors off. But there you go. Yeah, this is a good way to look at it, actually. I'm glad you mentioned that. It works on smartphones. Yeah, this should work, yeah. It's HTML5, so it's designed to work on pretty much any platform. Anything should work. Yeah, actually, this is a good thing to look at, because you can notice something here. So, this x velocity, right? We noticed it didn't change. The y velocity, though, is this one that points up here, and then the yellow is the acceleration, okay? So y velocity on top, acceleration on bottom. If you think about it, what is that acceleration vector doing? It's constantly changing the y velocity, right? So since this points down right now, the y velocity, even though it starts up, it's going to get smaller and smaller and smaller, as you can see here, until it basically is pointing in that same direction, right? This is part of why you can say that you can split this motion up, is because that acceleration vector says that there's going to be a change in the y velocity, not the x velocity, because it only points down, right? Okay. They point, yeah, vy in the a direction, right? Yeah, the change in the velocity in the y direction is in the a direction, right? All right. So let's talk about some of the kind of things that we got from that. All right. So there's no shape for no, of course there's not. Okay. So let's just start off with a shape for the ground, and we'll try to do our best to draw projectile motion. All right. So take an object. We got a ball. It's launched from down here. We give it an initial velocity vector that we say points up like this. Let's just do one like that. So here's the way we're going to define these things. We're going to call this the initial velocity, like this. And we're going to say that the angle that's made between that and the horizontal, I guess I should drop another line in here. Here, what we'll do is we'll put the ball so that it's right there. I'm going to call the angle that's made right here theta naught, although I might not always do that. I may just call it theta sometimes, but for now we'll call it theta initial. Object launches with an initial velocity in this direction with an initial angle like this. And now we'll draw the path that the object goes on. The path should be something like that. That's awful, but it's about as good as I can do on the computer. So now we've got, that's kind of the path of the object. And we can start talking about what's going on in this system. So we know some things from what we just saw, right? Some things that we know about this system is that the x-coordinate of the velocity is a constant. Oops. We also know that the y-coordinate of the acceleration is a constant. I'm going to say that it's equal to negative g, okay? Where when I say g, I basically just mean, I'll put it up here, that g is going to be equal to, 9.8. Notice that I'm saying g is a positive quantity, but I'm saying the acceleration is negative g. Oh, and this is positive y. This is positive x. All right. If I choose some point on the path right here, this is going to be the direction of my velocity vector. It looks so bad. I need to draw these vectors with the thing right here. So if I pick some point on my path, my y velocity is going to look like this. I'll be able to split that up into components. There's going to be a component that points in the y direction and the x direction. So let's do, here, we'll do x direction first, like this. We'll make the direction in the x direction green. And then the y direction, it's going to have a component that's going to point. I don't understand why it does that, but whatever. So that's blue. So these are going to be Vy here and Vx right here. We'll define the angle that's made between, oh, and then this is the velocity vector right here, right? All right, so we know Vx is constant, Ay is equal to g, and we can basically use this information to start describing what this motion does and to start writing down equations for it. And because the acceleration is constant, we can use the kinematic equations to describe what's happening here. So for example, what we can say is that in the x direction for this motion, we know that the position or the displacement of the object has to be equal to the x component of the velocity multiplied by time. And we also know that if we look at the starting point down here, I don't know how well I did this, but if I did it somewhat well, then I should be able to just copy paste this down here. It's not bad. So this would be the initial x velocity. I'm just going to call it Vx since it never changes. And then we can define this over here to be the y velocity. We'll call that the initial y velocity. So we'll call that vy and then put a 0 here to represent initial. All right. But when we look at that thing right there, it should be pretty clear. What is Vx equal to? It's going to be equal to V initial multiplied by what? We'll use cosine of that angle right there, theta naught, right? Okay, so this equation then can be written more generally as saying that the displacement of the object is equal to the V initial times the cosine of theta naught multiplied by time. Any projectile problem you do, this is always the equation you're going to use for the x direction, okay? It's basically constant uniform x velocity, right? Oh, and I guess I should be a little more clear here. If I drop a line down here, then delta x is this distance, right? That's what I mean by delta x, okay? And delta y would be this height, this distance here, from here down to here. That would be delta y. So that's all we need to know about the x direction. And just remember this. When you get stuck in problems, just write this down, okay? Remember that this is something you can use. It'll be very helpful to you in many problems. Okay, what about the y direction? In the y direction, if I want to talk about the displacement, delta y, I'm going to have to use one of the kinematic equations, right? So delta y is equal to Vy initial times time plus 1/2 times the acceleration in the y direction times t squared. I don't care about acceleration in any other direction except for the y direction when I'm talking about y. So we can write this, and we can use this, and we can also use the fact that Vy initial, what's Vy initial going to be equal to in terms of these variables over here? It's going to be V naught multiplied by, not cosine, but sine now. So we can plug that into here, and what we end up getting is the delta y is going to be equal to V initial times the sine of theta initial times time. And I'm going to write this as minus 1/2 gt squared. Because the acceleration is negative g, right? So you can write it out like that. So that's going to be an equation when you're doing projectile motion problems that you can use as well. And then we can also talk about the other variables that show up here, like Vy and Vx. So we've already talked about Vx. Vx doesn't change. It's the same here and up here. But Vy does. So we can say for Vy, if I want to figure out what the y velocity is at some point in time, like right here, for example, you can just say that that's going to be equal to the initial velocity in the y direction plus the acceleration in the y direction times time. That was one of our kinematic equations, right? And this equation can be simplified in the same way by saying Vy initial is V naught times the sine of theta naught multiplied by t, and then you just do minus g times, oh no t here, my bad. So then minus g times t. And that's another equation you can use. And the final thing I want to do, does anyone have any questions? Some of this stuff should be pretty familiar to you. What I want to do now is I want to combine these two equations here to give you another equation that I think is very, very useful. So to combine those two equations, what I want to do is I want to eliminate t. All right? So first thing I'll do is say from this equation that's heavily underlined here, I can rewrite that one as time is equal to delta x divided by V initial times the cosine of theta initial, like that, right? Just basically solving that equation for time. And then I can take this and I can plug it into this equation here for t. So that's what we'll do. So we'll have, let's scroll down just a little bit here. Okay, So I can write delta y is equal to v initial sine theta naught times t, but for t I'm going to plug this in. So we multiply by delta x and then divide by v initial cos theta initial. And then it's minus 1/2 gt squared, so minus 1/2 g. T is this, so it's going to be delta x over v initial cos theta naught whole squared. And we can expand this out. So the first term right here, the v naughts cancel in that. We have sine theta naught over cosine theta naught. What's that equal to? Yep, tan theta. So delta x times tangent of theta, it's theta naught, minus, I want to write it like this, delta x squared times g divided by 2 v naught squared cos squared theta naught. All right. So that's our expression. All of that is equal to delta y. Delta y is equal to all of this stuff right here. Let's write this final equation here in black or something like that. So if we look at that equation, it tells us something about this motion. And we could write it in a way, I think, that might look a little bit easier to read. So let's say we pick y initial equal to 0 and x initial equal to 0. Then since delta x, for example, is equal to x minus x naught, delta x would just be equal to x minus 0, which means delta x would just be equal to x. And by the same argument, delta y would be equal to y. Does that make sense? If we just say y initial is 0, then change in y will be described as just y, right? Because y minus 0, right? Then the entire expression gets written as y equals x tan theta naught minus x squared. And then I'll just copy paste this piece down to save some time because we're running out. Take a break soon. It's the last thing we're going to do, and then we'll take a break. So if we look at that expression, let me move it down just a little bit. Okay, if we look at that equation right there, what do you notice about that equation? Keep in mind that theta naught is just a number, right? G is just a number. V naught is just a number. All of the things in this parenthesis are just some kind of a number, right? Same thing with tan theta naught. So, for example, I could rewrite this equation like this. Y is equal to x times, I don't know, tan theta could be something like 2 or something like that, minus x squared, and maybe when you multiply all this stuff together, maybe you get 10 or something. I don't know. What does that equation look like to you? If we wanted to plot it, for example, y as a function of x, what kind of equation is that right there? It's upside down parabola. Exactly. Yeah, exactly. That equation is basically just this, right? It's a parabola. So what that tells us is that when an object moves as a projectile, such that gravity only acts down on it, and there's no air resistance, then the path of the projectile is going to be a parabola. And we kind of just proved it there, basically. Because you've got, y as a function of x, and you've got a x here, and then a negative x here, and it's a negative parabola. Upside down is important, as you guys said, because there's a negative sign there. So there we have it. Good place to take a break. Does anyone have any questions? We'll come back and we'll use these equations to solve problems. This equation is very, very useful for when you don't know anything about time. You know what I mean? You don't know anything about time. This equation is extremely helpful, okay? So I'll say that.
I'll try to repeat it so you remember it, but if you have a problem in which you're given, let's say, I'll just put it up here. Let's say in a problem you're given the following variables. You know, actually, I'll give you exactly the kind of problem it's going to be like. Let's say I have an object, okay? And the object is launched right here with some initial velocity, and it goes and it strikes like some point, like let's say this is a mountain right here or something like that. And all you're given is the XY coordinate of this point right here. Okay? And maybe you're also given this angle. Oh, no, you don't even need to be given the angle. That's right. So suppose the question is this. Suppose this is the kind of question you get. I have some projectile launcher. Okay? I have some projectile launcher. Maybe a cannon or something like that, or a gun or an arrow. And I know that I want to hit a coordinate right here. Like maybe I'm launching a supply package to some stranded hikers that are up on this mountain. Okay? And the way I'm doing it is by launching a projectile. And all I'm given are these two quantities here. I know how high they are, and I know how far away they are. Okay, so I know X, and I know Y. And the other thing I know is how fast my gun can shoot. Okay? And I want to know what is the angle I need to shoot at. Okay? If this is the kind of problem you're given, that equation will solve it for you. Because you can see you have Y, X, you've got the initial velocity, you've got G, obviously, but this is your only unknown. Now, of course, you're going to have to solve for theta naught, and it's not going to be easy. But you can do it, right? It's not as hard as you think. We're going to look at problems like that later on. So this equation is very useful because it does not have time in it, and it relates y to x. Okay, let's see the questions we got here. So if you take the second derivative of the equation alone, we can find the acceleration below. Yeah. So even when x naught is not equal to 0, the graph is... Oh, yeah. It's still a parabola. Absolutely, Summer. Absolutely, yeah. It's still going to be a parabola. Okay, let's take a break. It's 3:09.